Greetings, let's have a quick proof here. It's not that simple one, but it's quite straightforward. So let's have VW finitely generated vector spaces and B basis of VC basis of the other vector space W. And we have a linear map that goes from vector space V to vector space W. And then we have kernel F is of course subspace of V, and it in respect to B is going to be equal to kernel of this matrix of F in respect to B and C. And image F is a subspace of W, and it applies also image F in respect to C is image of F in respect to BC, like this. I only verbally mentioned that kernel F is a subspace of V and image F is a subspace of W. All right, so that's also, but nevertheless, that's also worth to mention, just not written down. Well, the kernel is unempty and closed for addition, because we know that this applies. We have f of u plus v actually equals f of u plus f of v, which would be 0 plus 0, which is 0. And so u plus v are inside the kernel of f. And we do the closedness, or it's closed in relation to multiplication by scalar exactly the same way. We can do that equation as well. And let's move to the next part. So let's realize that kernel F in respect to this first part here, and the scalar part was just mentioned, kernel F in respect to B, we can actually write it as all x's in respect to B, such that f of x is 0, is mapped to the 0 vector, which is the same as all vectors v in respect to B, such that f of, so this is the matrix of f in respect to B and C times vector v in respect to B is equal to 0. And we have that's equal to kernel of f BC, like this. Well, evidently the image is unempty, and we can check its closeness if W1 and W2 are inside image F. Then there exists some V1 and V2 in V, such that f of V1 equals W1 and f of V2 equals W2. So let's write it out. So check closeness for addition. I won't write it out. Let's just say if these two are in image of F, then there exists V1, V2 in V, such that f of V1 is W1 and f of V2 is W2. And by linearity, we have f of V1 plus V2 actually equals to f of V1 plus f of V2, which is W1 plus W2. I just skipped that step to save some writing time. And the closeness for multiplication by scalar is exactly the same idea like we did with the linearity, just putting it algebraically there. And we also have a theorem regarding the matrix of a linear map. And we know that image F, so this is the next step, in respect to C is actually this f of V, each f of V in respect to C, such that V is inside the vector space, all right? So going over all the V's in the vector space like that. And that is the matrix of the map in respect to B and C times V in respect to just B, all right? And as V ranges the vector space V, which is actually equal to the image of F in respect to B and C, like this.